There's one last thing I want to discuss in terms of Snell's law. So we've used Snell's law to build a lens where we look at light being transmitted and focused by a lens. But Snell's law can also give you perfect reflection, and here's how. We're imagining a situation where light is going from a material with high index to low index. So we're starting in, for example, starting in glass and going to air. So some of the light is refracted, and theta 2 is larger than theta 1, and some of the light is reflected at angle theta 1. Now if we make the angle theta 1 larger and larger, eventually this angle here will be 90 degrees. So the light that is refracted, the light that is transmitted, comes out and then travels parallel to this surface. If we increase this angle theta 1 even further than that, there'll be no more transmission. All the light will be reflected at theta 1. So what's happening mathematically to this Snell's law? Basically what happens is we find a situation where the equation for sine theta 2, so this is the equation here for sine theta 2, gives us a number larger than 1. So sine theta 2 is larger than 1. You can't find an angle, a real angle, theta 2, such that this equation is satisfied, so the light that is transmitted goes away and all the light is then reflected. So we call this total internal reflection, and beyond some critical angle, all of the light, 100%, will be totally internally reflected. This total internal reflection angle, the so-called critical angle, is given by theta 1 equal to the arc sine of n2 and n1, where n1 is greater than n2, and for all angles greater than this critical angle, we have total internal reflection. So total internal reflection has a number of important technological applications. One of these, it's kind of the basis of optical fibers. So an optical fiber is built like this. You have a core with refractive index n1 and a cladding with a refractive index n2. These are both kinds of glass, but the cladding has a slightly lower refractive index than the core, so that light coming along through the core can be totally internally reflected. Now in real life it's a little bit more complicated than this, because the core here is only a few microns across, and so when you get to sizes of the order of their wavelength of the light that we're thinking about, then thinking of it in terms of total internal reflection is not the whole story, but the essence of the physics is there. So total internal reflection guides light down these pipes, and there's going to be some maximum input angle here, and as long as the light coming in is less than this angle, then it will be totally internally reflected off this surface here. And you can show this maximum angle is given by the inverse sine of the square root of the difference of the squares of n1 and n2. And if you want to put numbers to that, for a typical telecommunications fiber, n2 is given by 1.444, and the ratio of n1 to n2 is actually very close to 1, so the refractive index of n1 is only slightly larger than n2. And so you can calculate the maximum input angle for this telecommunications fiber. Another application involves sensing. So when we think about total internal reflection, we think about light coming up to the surface and being totally internally reflected, but above the surface there is still some field. In fact, the field decays exponentially away from the surface. So the electric field amplitude decays proportionally to e to the minus beta y, where y is the distance away from the surface, and beta is given by this equation here. And this is the evanescent field, and although there's no power carried by the evanescent field, it's quite real and it can be used to build optical sensors. So for example, you can imagine a waveguide with light being guided along through this waveguide, and this is the guided mode, so the light has some shape like this, and above the surface here there's some evanescent field. So if you imagine the light there, it's kind of being trapped in this waveguide by total internal reflection, it forms a mode, and some of the mode is existing above the surface here, and we can put some receptors that detect proteins and biological sort of markers, and the light inside this waveguide is sensitive to that because some of the mode exists above the waveguide. Now I just want to be clear here that in the case of total internal reflection, this ideal case, all the photons are reflected. So every photon coming up to this boundary is reflected back down into the medium n1. But that does not necessarily mean that the field in n2 is completely zero. So it's decaying exponentially, and we can interpret this as the photons sort of probing this area n2 and then in the end deciding to be reflected. And this gives rise to this evanescently decaying electric field where the photons while they're not being transmitted, nevertheless do sort of probe into this area above the surface.